Alright, you need to pay attention because this one could get a little hairy, but you gotta make sure you understand what's going on. In the previous notes that we discussed, we were talking about angles and arcs, the relationships between those. If it intersects inside the circle, how you take the arc and you add them together and divide by 2, and it'll tell you that angle there, or the same thing for those. Or you take the outside arc here and subtract the inside arc and divide it by 2 on either one of these pictures. But notice that we're looking for the angles here. We're focused on the arcs and the angles in this particular note and the ones that you did yesterday or whenever you did those. Today we're talking about the segment lengths. The segments are what we're discussing today. Segment lengths. So we're not talking about angles. So you have to know which question or what part of the question is the issue. Are we talking about angles and arcs, or are we talking about segments? And so you need to know that based on the instructions. Here's some definitions. Segments of chords. It's basically when you got 2 chords and they intersect, they go into segments. So here's 2 chords, and AE is a segment, EB is a segment, CE is a segment, and ED is a segment. A secant segment is basically the same thing, but part of it goes outside the circle. Read the directions here to make sure you understand, the definition here. And an external segment is a part of a secant segment that is outside the circle. What I suggest everybody do is pay attention to the picture. On all of these is understand what the picture is saying. Here's our first theorem. If 2 chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of another chord. Now, most of us don't talk like that, so let me translate. The idea is if you have 2 chords intersecting inside a circle, then the relationship that exists is each segment of the chord. If you multiply one segment together, it should equal the other segment multiplied together. So this part here, AE times EB, should equal ED times EC. And that's the relationship that these have. The pieces of the segment of one segment you multiply, and it should equal the pieces of the other segment. So if this was 1, and this was 2, and this one was 0.5, and this one was 4, then they should equal each other. 1 times 2 is 2. 0.5 times 4 is 2. Okay, that's a silly example. Let me show you a better example. In this particular example, we want to find JK. Alright, so we need to find the actual length, so that means we need to know X. And so the way this would work is you would set this equation up understanding the theorem. The theorem says that LN, this section right here, times this part should equal X plus 5 times X, or this part right here. So let me do that. That'll be X plus 3 times X plus 1 should equal X times X plus 5. So what am I doing? I'm using this theorem that says that whenever you have these pieces like that, then the relationship is that the segment parts, this part, LN, and then MN multiplied together. See, all that's one segment. You don't interact different parts of the segment. This is not similarity where you put this part over this part. It's not like that. It's this segment times this part of that segment equals this part times that part. Now, how does this work? Now, I'll try to keep problems like this away from you guys, but the way this works is you have to multiply these two, which is called a FOIL. And I'm not going to bother you guys on understanding how to do a FOIL now. You should learn that next year, or we'll talk about that maybe after EOIs. But this is distributive property. And so when you multiply, you will get this times everything and this times everything. But notice these two middle terms will combine. So you have x squared plus 4x plus 3 equals x squared plus 5x. Now, in order to solve this, you have to combine like terms. So I'm going to put everything together on one side that's like terms. But when I subtract my x squared from both sides, notice that they cancel out. So I don't have to worry about that. So I'm left with 4x plus 3 equals 5x. All right, 4x plus 3 equals 5x. And then solving for x, I just subtract 4x from both sides, and I get x equals 3. So x equals 3 is what x equals, but in order to find ML and JK, I have to know what x is. So what I'm going to do is put 3 plus 3. What am I doing? I'm substituting x right here, and I get 6. Then I do 3 plus 1. And I get 4. So 6 plus 4 is 10. That's LM. Now let's do JK. If I do 3 plus 5, I get 8. And if I do just 3, because there's no addition here, it's just 3, so that equals 11. So JK equals 11. Now let's actually prove that this property works. Okay, let's prove that this theorem works using just numbers. Okay, so if this part right here, ln is 6, let's just go over here. If ln is 6 and nm is 4, we will do 6 times 4, and that should equal jn, which is 8, times nk here, which is just 3. So is that true? 6 times 4 is 24. 8 times 3 is 24. Yes, it's a true statement. All right, so the answers here is LM equals 10 and JK equals 11, which tells you that they don't have to be the same chord. They don't have to be congruent chords. It doesn't have to be that way. But their products of their segments have to work. All right, let's keep going. There's more. All right, so this next one says when you got a segment of a secant, if two secant segments share the same endpoint outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other external secant segment and its external segment. In plain English, what this says is, notice that they're intersecting outside a circle, and I'm not looking for an angle. I'm looking for the lengths of the segments. The relationship says the outside part times the whole thing equals the outside part here times the whole thing. And so we're going to do that, we're going to prove that looking at this example here. Let's move that over a little bit. Okay, this example here says find the value of x. So the way this would work is I would say the outside part, which is 6, times the whole thing. Well, what's the whole thing here? It's not 4. It's 6 plus 4, which is 10. That's how you would work that. All right? So it's outside part, the part that's outside the external part of the circle, times the whole thing, which is 10. And that equals this side, the outside part 5 times the whole thing. Now notice there's an x here. So the whole thing is not 5x. The whole thing is 5 plus x. And so I'm going to write 5 plus x. You're going to have to make sure you remember that and figure that stuff out. There'll be problems like this. Outside part times the whole segment. Outside part times the whole segment. Doing the math on this, and for the sake of time, I'm just go ahead and get to the answer. So once you solve this, distributive property here gives you 25 plus 5x. Solving for x, you get x equals 7 here. And that's all they wanted, was for me to find the value of x. So again, this property basically says that the outside segment times the whole segment equals the other outside segment times the whole segment. What about if it don't go through? What if you just got a tangent, okay, and a secant segment? Well, this part is still the same. It's the outside part times the whole thing. But this part, you have to square. That's what it's saying. If it's a short part like this, that's not a complete secant that goes through the circle. If it's not a secant, then what we do is we simply take the outside part that's not a secant and we square it. So how does that work here? Looking at this example, how would that work? Or what would that look like? Well, we would say 14 squared. That's the tangent part that's not going through the circle. So we just square that, and that equals the outside part times the whole thing, which is x plus 12. Alright? So it's the outside part times the whole thing, which is x plus 12. And that equals 14 squared. Alright? That's how we will set up this problem. But looking at this particular problem, in order for you to work it, you're going, well, we should be able to, no. You got to know how to FOIL here. So I'm going to try to, and factor and stuff, things that we haven't talked about. So I'm going to try to stay away from problems like this, but I'll go ahead and set it up for you so you can see how it works. And that's about as far as I would go. I just squared that, distributed property there, moved everything to one side. This is called a quadratic equation, and we haven't really talked about these. And so I'll just leave it at that, and we'll move on. But that's how you would use this property here. Square that short part, and it equals, like before, the outside part times the whole thing. All right, real quick, here's another example of a problem like that. Here's the answer. Let's see if we can prove it. We have the little short side, and the way it works is we would say 15 squared equals the outside part times the whole thing, which is 9 plus x, or x plus 9, the same thing. All right. Now, again, for the sake of time, I'll just show you the answer here. All right. So you see, after you square this distributive property, solve for x, you'll get 16 here. And so the issue is, do you know how to set this part up? That's the issue. The rest of this is just solving, which we should be okay with. All right. Let's move on to a different type. Let's look at number 5 here. You might have to look harder or zoom in or something, but this is the segments, the chords that intersect inside the circle. And the way you would set this up again is the parts of the segment multiplied equals the parts of the segment multiplied. And so you could say something like 8 times 4x plus 2 equals 9 times 4x. Okay, I could use parentheses there. And again, let me pause and I'll come back to the answer. But again, the setup is the important part. Remember, multiplication is commutative. So if you put this in front of the 8 or the 4x in front of the 9, but you know it's multiplying, it doesn't matter. Okay, so as you see me work the problem out again, distributive property, and those two, solving for x, you'll see that x equals 4, and that's me using one of the other properties. All right. So again, the key is, do I know how to set this stuff up? And that's very, very, very important. All right. What about number 8? It's a little bit different than this one here, the first one I worked. And so let's look at that. Well, I can at least talk about the setup. And the setup is going to be 8x times the two combined. So the outside part times the whole thing, which is 14x. And that equals 7 times 16. Is that right? Yep. The outside part times the whole thing. All right. This is how we prove it as you work the problem. Multiply those two, and you should get 112x squared. 7 times 16 is 112. You divide by 112 in order to get the x squared by itself, and you'll get x squared equals 1. Take the square root of both sides, and that's how you'll solve that. Again, I'm going to try to stay away from problems that deal with you having to work much with the x squared, but we should be able to solve, because we've done Pythagorean theorem where we had to do the square root. All right, so if you got questions about any of these, let's talk about them in class.